Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Now, first question there is an English question again. What does that mean? For a couple of reasons. One, I need to prepare my students to communicate mathematically and to actually write, explain answers in exams. Two, I think it's much better if they actually know what that means rather than just being a mystic symbolism on the board. So, what is it saying? Find the area underneath the curve 2x plus 1 between 2 and 5. Now, that's what it means. So you're being asked to find the area of some shape. And will you use length by breadth? Will you use pi r squared? Will you divide it up into loads of shapes you really know? What do you do with it? Sure, you don't know what to do with it until and how are you going to know what shape it is? And really and truly, aren't we back to what problem solving strategy are you using? You're drawing a diagram for this one. Because when you're dealing with shapes, surely you need to see them. Junior cert teachers can teach their kids that. They come to leave insert, it's happening naturally here. So look, there it is drawn. Now, actually, the function y, or f of x, equals 2x plus 1. What is it? Straight line, intercepting the y-axis at 1, with a rise of 2 and a run of. So who should be able to draw that? Any junior cert student out there. Now find the area between that, the x-axis, 2 and 5. Look at it. What is it? Trapezium. 1 trapezium. Supposing you were only in junior cert. Could you find the area of that trapezium? Because trapezium isn't on the junior cert syllabus. But could you find the area? Yeah. You're back to that. So that activity, who could I give it to? I could give that to junior certs. And I'm testing stuff on the junior cert syllabus. Okay, what's the only thing I couldn't have there? Instead of integral between 2 and 5, I would have to say, find the area underneath the curve, the x-axis, between 2 and 5. But with that there, junior certs could do it. Would they be revising? Would they be studying material on the syllabus? A lot of it. And what are they doing? A leave insert integration question. There's only one step forward when they're in 6th year. But that's a notation for all that big long English. That's all. Look how you could shorten the syllabus at leave insert level. And this is just integration. I'm saying in most areas, if things are taught in a certain way at junior cert, using certain activities, they can be reused and built on at leave insert. And there's the syllabus shortened for you. If the junior cert teachers don't want to or aren't interested enough in interacting with the syllabus as it should be, then that's going to create massive problems for the students at the later level. And that's the reason I'm saying, thanks be to God, you are all interacting with it. But I think you can see how much you can learn as a junior cert teacher about the way you might teach elements of the course to assist the students the whole way through. So look at this question. Now, this would be on a higher level leave insert paper, okay, but I think everyone can work through this with me. Using 4 equal intervals, approximate that. Now, you know, most people run away from that because it's symbolism. But read it for what it says. Using 4 equal intervals, approximate what? The area underneath the curve, the x-axis between 0 and 4. At leave insert level, what's your tool for approximating area underneath the curve? Trapezoidal rule. So what's that a question on? Trapezoidal rule. Where are your 4 divisions? 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So that's actually quite an easy question. Where do you get the heights? They're the y values, and by the way, what's the function? So where do you get the heights? They're the y values. Where do you get them? So because it's not a measurement one here. All stuff that has been done almost at junior cert level. Now, this is the more difficult, I suppose. Look at that. Calculate the exact value of that. Now, can I maybe talk specifically to higher level leave insert teachers for 1 second? How do you integrate that? Or how did we? It was a substitution method. It was a sign substitution method. And when you made the substitution, it was still a pretty hard integral to work with. Is that substitution method on the syllabus now? It's not. Now, I suppose if you want to, you can teach it. But if you start teaching stuff that's not on the syllabus, where do you stop? So we need to look at this another way. What have you been asked to do there, really? You've been asked to integrate something that you don't have a technique for integrating. Do you remember I said that at the start of the presentation? You're actually being asked to integrate something that they will not have a technique for integrating. So what do? This is where you have to have the understanding. What have you been asked? Forget integration. You've been asked, find the area underneath that curve. What curve? Give me another way of writing down f of x. Don't know about you lads, but I hate square roots.
Square roots.
What's that? Equation of a circle, centre, radius, what's the area? Pi 4 squared. Why were you doing a sign substitution, changing limits, and still having something awkward when that's what you could have been doing? Now, this comes back, I would say, to my junior cert thing. If I'm finding an area of a shape, I would like to see what the shape actually looks like. And with the square root there, what square root is that? The positive square root, the negative square root, or both? It's just the positive. And if you're talking about y values, where are y values positive? So actually, no, it's not the full circle, 'tis only half it. Excellent, but hold on a second, look at it now. It's actually between 0 and 4. So it's a quarter of it. Now, that to me, that's the extra little bit that the junior cert teachers, I think, can prepare people for. If we're looking for area shapes, we should have our problem-solving strategy of actually drawing them. And if we do draw them, we'll see those 2 little catches. The other thing was, when you don't have a technique for doing something, how do you deal with it? You go back to your understanding. What's really going on behind the scenes? Do you remember the trapezoidal question about the estimate? The only way of answering it was really to know what was happening behind the formula. The only way of doing this now is know what's happening behind the scenes. And that's the testing for understanding, and that's why we have to do more than just give our students techniques and give them 40 to practice. Now, next step. I have a way of calculating perfect area underneath the curve now, but it's really difficult. Because to find the perfect area underneath the curve involves me having to calculate this thing here, which is a big limit, and it's difficult to do. So I'm going to try and simplify that, efficiency and effectiveness. And what I'm going to try and do is something that we did in Workshop 8, and I demonstrated it earlier on. In Workshop 8, to try and get an understanding of differentiation, we created a function. We created the slope function. And that was what taught us about differentiation. Because functions are great. If you have a function, you can just get answers by plugging in values. So if I could get an area function, it would be brilliant. Because if I could get an area function, I wouldn't have to bother with this. And I could just plug numbers into my area function. So that's what our next activity is going to try and do. We're going to try and come up with an area function. And then when I'd say, find the integral, all we'd have to do is plug in values. Now, the teaching and learning plan to do this has 5 activities. Would you be surprised to hear that they're called A, B, C, D, and E? And what you probably do in your class is get each table, each group, to do one of the activities. We'll just look at one of those. We're going to look at activity B, and it's in the workbook on page 11. And what you've got there on page 11 is the picture of the view bar in Dubai. Question, we want a kind of an idea of the area of the face. So what do? We model a function for the roof, just like we did with Ballymun. You don't have to worry about that. I did it there for you. It's the graph on the left-hand side of question 1. What is it? What's that graph? What's that function? Well, what type of function is it? And if it's a straight line, it's y equals mx plus c, but it's gone through the origin, so c is 0. What's the rise and the run? And for a run of 1, you have a rise of 1. So what's the equation? Y equals x, or if you like, h of x equals x. Now, what the activity does is, look, I've marked off a little area under the roof, just a tiny little bit of the area under the roof. And I've asked, what is that area? Well, what shape is it?
Triangle.
And what's the area of a triangle? And what's the base? Is it, yeah. And what's the height? So what's the area? Half 1 by 1. To be honest, I don't even care about the answer. It's a half 1 by 1. Now, will you continue the rest of that activity? And the first one we had done, and the area was a half 1 by 1. And then the second one, the triangle got bigger, so the area was half 2 by 2. And we asked to continue that procedure over in question 4, but it's done out in a table because higher level leave inserts by 2 examples, they should see what's going on. So filling in that, I was looking at people, I think most people have filled it in okay. When x was 0, the width was 0 and the height was 0. When x was 1, the width was 1 and the height was 1. When x was 2, so basically you're filling in that table with the widths, the heights. Now, I swapped the slide around from the workbook, because in the workbook you were kind of asked for the answer first and the pattern second. And the pattern was really the formula, which doesn't start to make a whole pile of sense. So I switched it around and I have the pattern first, and I think it's the more sensible approach. So we've seen that the area of those triangles, half 1 by 1, half 2 by 2, half 3 by 3, etc. But going back to what we had earlier this morning, kind of what's the natural reaction when you've got a table of values coming from the problem solving strategies, what they're doing at first, second, third year, trying to spot a pattern. So when the x coordinate is x, what was the width? And in each case, it was the same. What was the height? Because the function was h of x equals x, the heights were the same. And what was the area? A half x by x. So now, which is a half x squared. And now we've got a function that will calculate the area underneath that line for us. So we needn't bother going back to drawing rectangles or trapeziums. We needn't bother going back to the limit thing anymore. We now have a function that will tell me the area underneath that. It's the area function, half x squared. Now, you might have one or two bright students in the class. That was h of x equals x. And the area function for x is a half x squared. Any little penny dropping. And there may or there may not be. Some students might see where we're going with this straight off. Maybe to help them even see where it is going, you could always graph the area function if you wanted to. And there's the area function being graphed. And notice a linear kind of becomes a quadratic. Or if you looked at that the other way around, a quadratic becomes a linear. Maybe they're beginning to see something link with what they've already done. So now we have this question to answer. Read it. And what's it saying? Find the area underneath that curve there between 0 and 3. That's really what it's saying. But we now have an area function. So what's the easiest thing to do? Plug 3 into the area function. In other words, get the value of the area function at 3. You could read it off the graph if you wanted, or plug it into the function. There's your answer. So we actually don't need to go back drawing the rectangles anymore. We don't need to go back to the limit anymore. We've become more efficient and more effective now that we have found an area function. So answer that question. Find the area underneath that line from 0 to 5.5. Quickest way of doing it, we have an area function. It's the value of the area function at 5.5. Read it off the graph if you wish, or plug it in, whichever. But next comes the interesting question. This one. And again, read it. Find the area underneath the function between, which one do I plug in? Hold on a second, maybe we should look closer at what we did earlier.
Get the big one and then take the smaller.
We went from 0 to 5, and that goes from, it's the whole lot. Next step is to take the feedback from the 5 groups, A, B, C, D, E. Each group worked with a function. Each group has got a corresponding area function. So we have a table of values there. What's the natural instinct when we see a table of values? Look for some link, look for some connection, look for some pattern. Now look, 5, the area function is 5x. Original function is x, the area function is a half x squared. The original function is 2x, the area function is x squared. Do you see a link? And I'd hope some students will, but if they don't, what I might say to them is, look at this and go that way. 5x becomes 5. Half x squared becomes x. X squared becomes 2x. 9x minus 27 becomes 9. What's going on? Going that way? Differentiation. And they're the functions that you had in the very first activity. So what's it going this way? Anti-differentiation. So this is a magical moment now. People should be dancing in the aisles now, because what we've just sort of discovered is that I can use antiderivative as a tool for calculating area. They're not the same thing. We saw them being derived. Antiderivative is the reverse process of differentiation. Integration is find the area underneath the curve. But now we've just discovered that I can use the antiderivative to create the area function to do the integration. And that's the link between the two of them. A link that we have seen in other sections before, reading normal tables. What are you doing when you read normal tables? You're calculating probabilities on the basis of area underneath the curve. And you know the way in reading the normal table, sometimes you had to subtract one value from another. And by the way, look how you calculate the area underneath the normal curve. It's an integral, because it is an area. So try and pull it all together now with a question. Here's another building, and I'm the window cleaner on this one as well. And I'm responsible for cleaning the section between 2 meters in and 6.5 meters in. So let's have a look. I'd need a function. There it is. Geogebra gave it to me. You don't have to worry. The question will give you the function, or it will give you enough information to derive the function. So there's the function. I'm responsible for cleaning the windows between 2 meters in and 6.5 meters in. So what area am I going to be responsible for cleaning? Write it down in maths notation, and what does it look like? The integral between 2 and 5, the function dx. Or if you like, find the area underneath the function p of x between 2 and 6.5. How do you answer that question? Using area functions. So it will be the value of the area function at 6.5 minus the value of the area function at 2. But what did we just discover? The light bulb moment. The area function is really the antiderivative. And how do we write down the antiderivative of little p of x? So it will be capital P of 6.5 minus capital P of 2. So if there's my function p of x, what's the area underneath that function between 2 and 6.5? It's the antiderivative evaluated at 6.5 minus the antiderivative evaluated at 2. Now we always taught them that, but why was it so? Now we can actually understand why it's happening. So find the antiderivative, fill in the values, and oh golly gosh lads, we have C there, but it's there twice. And in this case it's, and in this case, and that's the way it's always going to be. So actually, if they're always going to cancel, when we're calculating area, because they would always cancel, then we can dispense with the C altogether. And that's what's known as the fundamental theorem of calculus. A thing of beauty. The area underneath the curve can be worked out by finding the antiderivative and filling in the limits. So antiderivative is a tool for calculating area. Is that okay? So that's that middle section of it completed. And the last section was using area as a tool for solving problems. And the problems could be any type at all where you're adding up something. Because we've just seen when you add up, it's really finding the area. So look at this question. It's in your workbook on page 17. But I think, will we work through it or talk through it? All right, look at question 1 there, so on page 17. Bernie has a savings account, and there's the details of the money inside in Bernie's savings account, and the question is to calculate the average amount of money in Bernie's account. How will I do that, if I can do it? Say it. Add them all up and divide by the number of months in this case. And there 'tis done. They're all added up, divided by the number of months, got my answer, go home and have a cup of coffee. Nothing major there, is there? Let's look at the next question though. The next question asks, on a certain day in Cork, air temperature is described by the following function. Now, there's an issue with that function, there's a misprint. It can't be capital T because we know what capital T stands for. So, can we change that capital T to maybe an F just for function? So, temperature in Cork is described by that function where T is between 9 and 16. That's small t, so that's okay. Now you need to change this next bit where F is temperature in degrees centigrade and little t is time since midnight in hours. So if little t is time in midnight since in hours, what does 9 to 16 really mean? 9 in the morning to 4 in the afternoon. So we're trying to find the average temperature in Cork from 9 in the morning to 4 in the afternoon. Do you want to do it? Do you want to tell me how to do it? Do you want to tell me if you can do it? And if you can't do it, will you tell me why you can't do it? This data is discrete data. There's a definite number of them. So even if there's a huge number of them, you can still add them all up and divide by the number of numbers. But what's that? It's continuous data, as you rightly say. And if it's continuous data, what does that mean? It's always changing. So even if you took that function, got a table of values from 9 to 4 in the evening every hour, calculated the average using add them all up and divide by the number of observations, what would you be calculating? Would you really be getting the average? What would you be getting? So you're really only getting an estimate. How would you improve that estimate? I take it on the half hour, take it every quarter of an hour, take it every minute, but you're still only getting an estimate. So the question is, how would you get the dead exact perfect average? So can we go back to Bernie? This is Bernie. Now there was no problem there because it was discrete data. But let's look at Bernie's situation on a graph. And there's the graph of the money in Bernie's account. I hope the hole in the bucket isn't bothering anybody. Should it bother Leaving Cert students to see something like that? Or have they seen that before? Solving inequalities at junior cert, less than 6, you don't fill in the thing. So I mean, that really is junior cert work. They should be used to seeing that kind of thing. But let's look at the 8,000. What is the 8,000? Actually, it's a height. And the 8,000 is only there once, so it's only one time period. So actually that 8,000 is 8,000 by 1. It's height by width. It's actually area. Look at the 18,000. It's a height of 18,000, one time period in width. So it's actually height by width. It's area. 16,000 by 3. The 16,000 is there over 3 time periods. What are you really doing? You're multiplying height by width, so you're really calculating area. So when you add up all the numbers, what are you really doing? You're finding the area underneath the curve. And when you divide by the number of numbers, what are you really doing? You divide by the width. So give me another way of looking at average value. It's area divided by width. Do we normally look at it like that? We don't need to, because with discrete data we can always just do the regular, add them all up, divide by the number of numbers. But what about when we have continuous data? We need to add them all up. We can't, because there's continuous change. So can we look at average value another way? It's area over width. But what's the area underneath the curve? It's the integral of that function between the limits. And what's the width? It's the change in x. And what's the change in x in this case? 16 minus 9. So if you look at it in general, what's the average value of a function? It's area over width. The integral of the function between a and b dx over b minus a. Now that's the formula that we all have for average value. But now you can see why that formula actually works and why it does give the precise, perfect answer. Are we okay with that? And I think that kind of finishes our integration, our introduction to integration section. And that brings us on to the last session in this room, which is the nets section. So, talking about nets, as I was saying this morning, I think we'd probably be doing it in second year probably. And to prepare for it, I went into a class and I tried to see how what I'm saying would go with students. And the first thing I did was show that to the class and said, okay guys, what's that? Now you're second years, you're not adults and you're not teachers. Can you imagine the answers I got? What's that, lads? It's a carton, it's a box. Keep going. Juice. It's a juice. And someone yesterday said, "'Tis empty." What else is it? What else other answers might I get, or might I even hope to get? It's a prism. Oh wow, it's a prism. It's a cuboid. Yeah, I mean, of course, when you ask students something, you've got to be prepared for what you get, like, and you could get anything. And I did get the bulk of the things that you're saying. So we certainly got carton, and I got juice box, and I got rectangle, and I got cube, and I got a lot of other stuff as well. But the first discussion I'd kind of like to have is, of those words that I got, which do you sort of least like? Which would you prefer not to be getting? Who's wrong? Who's most wrong?
Well, rectangle is 2D.
All right, so you don't like rectangle because it's 2D and that's a 3D object, and I can kind of agree with you. Sorry? Cube is wrong because it's a, as you said, it's a cuboid, but at least it's 3D. Now, it is very much a matter of opinion, but I suppose I'd be saying this is a maths class and you should be talking maths to me. And for that reason, I think the words I kind of don't want to see is carton and juice box, because that's not even the vocabulary of the language that we're dealing with. And we want to try and give them the right vocabulary from the very beginning. Of what's left, I would personally think rectangle is worse than cube, because at least it's, at least cube is 3D. But cube is wrong, and what should it be? Cuboid. And you know, there always is one smart aleck in the room, usually somewhere down the back, who says, what's a rectangular prism, sir? So, actually, before I put that away, could I just ask you a question? What height is that? In centimetres, please. 12. 11. 15. 10. This is the strangest auction I've ever been at. It's gone up and down. Point I'm making, estimation is now on the syllabus. They have to be able to estimate dimensions, and students are not good at it. And we need to bring that into our classroom now, where we're teaching them how to estimate. I found it very interesting that not one person in the room picked up their measuring tool. You know, they have it in the desk and they won't use it. Actually, it's 11.5 centimetres. What's it across the top?
4.
It's 4.5. What's the here? It's 3.5. But my point is, estimation is on the syllabus. They need to be able to estimate. They're very poor at it. We need to be bringing it into our classrooms. We don't want to spend the whole lesson doing estimation. So maybe as we would pick up shapes or items, ask 1 or 2 students to estimate and give them the right answer. Over time, they'll begin to get a sense of what the values actually are. Talking about rectangular prism, would you expect a second-year student to come up with rectangular prism? So here's our connection with other curricular areas. Coming in from TG, they might possibly have it done there already and they would know it. Any other reason they might possibly know it? It's on the 5th class primary school curriculum. No, and that goes back to my prior knowledge point this morning. Just because it's on the curriculum doesn't mean it's done. Just because it's done doesn't mean then remember it. And are there any misconceptions there and gaps that they're bringing in with it? But we do need to access the prior knowledge again. If it's done in TG and they're all doing TG, I could be wasting 3 lessons here because they know it all already. And they might even know it better than me. But again, just because 'tis on the curriculum, I can't say, well, it's done, I don't need to bother with that, let's move on to what's next on the curriculum. So can I treat you as a group of second years and say, let's just check out that you do know your 3D shapes, folks. What's that? Now, I've tried this with students and I've been told it's a circle.
But you said 3D.
Well, I did say 3D and it says it up there, but like some people just have bad spatial perception. And even though I said 3D, they still can't see it.
There's a shading in the center.
You know, and there is, or is there, or do they understand that the shading, that's what the shading is indicating? You know, so look, why not have a football in the room and say, there? Because you need to have, for people who have perception difficulties, having a model is probably the best way over it. Some people learn better when they can just literally get their hands on it. What's the next one? I think here's the one they might have a problem with from the diagram again. So have the model, bring in the cornetto. What's this? Square base pyramid, and again I have my model. These are called polydrons. It's actually my niece's toy, and I think they're very good for doing 3D and spatial perception and going from 3D to 2D. So that's your square base pyramid. The next one is the triangular based pyramid. Then we've got, we've got triangular prism and hexagonal prism. So, can I just ask you, which of those are prisms? 2, 3, 5, 8, and 9. They're the prisms. How do I know that? Oh, that's an interesting question. How do I know they are the prisms? Well, if I suppose, how do I know? There's got to be a definition for what a prism is. So I need to know the definition. So that's the first thing. Second thing, are you all happy that they are prisms? Can I be blunt with you, because I feel we have a great relationship now, folks? You're wrong. There's one of those not a prism. There's one of those not a prism, and of course that comes back then to what's the definition, like what is a prism, so as I can rule things in or rule things out. Now the catch is the cylinder is not, I stress, not a prism. So let's look at it as to why not. A prism is a solid object that has two identical faces and all flat sides. A cylinder doesn't have all flat sides. What would your understanding of a prism have been? Say that again. The uniform cross-sectional area. And that would be a lot of people's perception of what a prism actually is. And under that definition, would cylinder fit the bill? It would, like a Swiss roll. But it's wrong. But if you go with that definition, is that a prism? Like, go with the definition as it's on the board. Has it two identical faces? Most certainly. Has it all flat faces? Most certainly. But like, from what, is it a prism? Why not? It doesn't have the uni. So that's not the whole story either. And you need the cross-sectional areas the same all along the length. You need both parts of the definition. But what has been happening is people have been taking one aspect of the definition, probably to simplify the issue, but finishing up giving the students a misconception. And I have seen posters on the internet that would have the cylinder on them as a prism. Then of course we know the shape at the end gives it its, so the Toblerone bar is the Toblerone box is a triangular prism. This is our hexagonal prism. By the way, what are they? Squares. All right. In terms of the shape though, what are these? Faces, not sides. Get the language and the vocabulary right. Now, out in the real world, is there a fair chance that people will say the sides of the box? Yeah. But that's the everyday meaning of the word. But side is a two-dimensional word, and it has length. When you're in 3D, these are, and they have area. So again, getting it clear for the students, the everyday meaning of the word and the mathematically precise meaning for the word. And you're back to this morning's idea again of literacy issues and the meaning of words. And when I say something, are the students hearing the same thing as I'm saying? Am I making it clear what it is? We need to be aware of those issues. Anyway, what is a net? Other than a very pretty lady. Say that again? A shape laid out.
Flat.
A shape flat.
A shape laid out.
A shape laid out flat. So there's a shape and I lay it out flat. No, you can see what I'm doing again. For these questions where they're going to have to explain answers, trying to get a level of precision into how they communicate mathematically. And you have nailed it. What is it? It's a 3D shape. So it's a two-dimensional representation of a three-dimensional object, and it's also called a surface development, bringing information in from another curricular area. So, like again, there is a huge cross-curricular link with this section. There's the primary school syllabus, and just pointing out that it does mention in 5th class 3D shapes, including tetrahedrons, would you mind? Faces, edges and vertices. So they should be coming in with the right language and vocabulary, but aren't they? Identify the number of edges, vertices and faces. Deconstruct shapes into nets. Draw nets. Construct the shape. So like, there is a lot of prior knowledge that they are supposed to have, but we need to check all that out. So things like looking at, we'll say a cube, they certainly should be able to identify the numbers of faces on a cube. Yeah? How many? The number of vertices on a cube, how many? Now again, you'll find students who can't see it on the picture. And you need to say, here, count them. You know, the corners. And then how many edges? And again, if someone is having difficulty, give them the model. So yes, there are 12. There is the syllabus, Leaving Cert and Junior Cert. And I'd just like to point out, investigate nets of prisms, polygonal bases, cylinders. If a cylinder was a prism, it wouldn't need to be mentioned separately in the syllabus. Why do we use nets? And of course the classic one is to help understand surface area and what it is. And that almost goes back to something that we were talking about this morning. So if you have something like this, which is your 3D shapes, it can definitely help you to understand the idea of surface area. Taking, for example, something like a cylinder, looking at its net, and investigating the idea of surface area. So what's the curved surface area of the cylinder? Well, let's see. There's the curved surface area. But actually, when I get its net, it's only. And the height of the rectangle is actually h, the height of the cylinder. And the length of the rectangle is actually and the circumference of a circle is 2 pi r. So the curved surface area is 2 pi r h. And you can see now why the formula is that. It's not this magical, mystical thing, as I keep saying, that the teacher just told me. They can see and understand why. Then you can discuss the issue of whether there are tops and bottoms to the thing, whether there's both a top and a bottom, or is it an open barrel or a closed barrel. I think those shapes are very good because you have those nets there and you have them for different shapes so that you can actually see what the net looks like when it comes out. those, I think Sligo provide them. You can get them on the internet, and any of the shops that provide educational resources will have them. And you have cubes and hexagons and cones. If I can just show you the cone one perhaps. You know, I think they are very, very good. And like a picture painting 1,000 words, a model, I think, paints 1,000,000 words. Another reason I think NETS is on the syllabus is anyone that has taught higher level Leaving Cert in the past will be familiar with some of those questions, the 3D trigonometry questions, and in general students were pretty poor at them. That particular one comes to mind. It was on 2006 paper, and a corrector I was talking to lately said that it was very, very badly done. And the reason it was very badly done is the students actually didn't realise that all they were working with was a square and 4 triangles. And if they saw that, the question was of no difficulty whatsoever. But if you think back to that old syllabus, NETs weren't on the syllabus. So as such, kind of the prior knowledge for that kind of a question almost wasn't there. If you were doing TG or woodwork, you probably had an insight, you had a better chance with that question. So putting NETs on the syllabus is bringing in the prior knowledge and the skills that would be necessary to deal with 3-dimensional questions. And I think for that reason, it's obviously a very good idea. Here's an interesting question about NETs, if you like, and it's about a cone. Higher level Leaving Cert, but I'd like everybody to engage with it. The first, you're making waterproof paper disposable drinking cups in the shape of a cone. And the first 3 parts of the question, they came up with 3 different cones. And I don't even care how they did it. But in part 4, they were asked to complete the table and fill in the dimensions of the 3 cones that they had just come up with, which I've done there for you. And then the question was, in practice, which one of the 3 cups is the most reasonable shape for a conical cup? Give a reason for your answer. So which of those is the most reasonable shape for a conical drinking cup? And give a reason for your answer. Now, first thing I'd be saying is there isn't much chance of teaching students 4 steps to answer a question like that. This is about understanding, it's about perception, it's all about skills that we have to now give them. Anyone throwing answers at me? C. You think C is the most suitable? Give me a reason why you think C is the most suitable.
Well, the first one is very shallow.
All right, now again, let's pick up our measuring tool. The first one has a height of 2 centimeters. I mean, imagine trying to even hold it. Okay.
The second one, then, let's say it's too narrow. If it has a radius.
Right, it's a bit narrow. Yeah, I can see what you're saying.
Yeah, all right.
yeah.
Okay.
But do you see the value even in asking students to explain, if it never came up on an exam? Because having had to explain it, he's just copped. Okay, with C, the radius is 7.5 roughly, but that means the diameter is, so if he's trying to hold it, he needs, you know, it's seriously big and uncomfortable and not practical to hold. Whereas this one, well, that's almost 9 on the top, which is reasonable enough with one hand, and the height kind of fits in as well. So it's a one-handed job. So a couple of things there. students' ability to estimate. They need to know what 2 centimetres is. They need to have an idea of what 7 or 8 or 9 centimetres is. That's back to the estimation skills that we're talking about. And now we have to practice it in class. Equally well, it's teaching students about taking everything into account. Because you rejected the first one on the basis of the height. You rejected the third one on the basis of the radius. So you're not just looking at one aspect of anything. And that was the suggested solution, which agrees exactly with what you have said. There's an exercise in the page 1 of the booklet. It's an exercise to test for the students. Can they see nets and the 3D object that goes with them? Now, I hope to God people can. Can we work through them? But just as you're working through this, it's page 1. Because I swapped the timetable around because I said we'd have the nets in the evening. As you're doing this, will you just see which way you're looking at it? Are you as an individual looking at the 3D folded out, or are you imagining the 2D folded up? Which way are you solving this problem? Are you going from 3 to 2D? Are you going from 2D to 3D? So, what's the net of A? 2 is correct, I think. What's the net of B? Is correct. What's the net of C? Where is it? Is correct. Back to my juice box. I took the juice box into class, second year group, and said, there's my juice box, folks. I'd like you to draw an accurate net of that juice box. So they have to measure. And that's the first thing. You'll get students who'll just go off and draw a net. Any old net, any old dream will do. So they needed to get the measurements first of all, or else they needed to ask me for the measurements, or if I gave them all a box, they needed to carry out the measurements. And that's on the course, like they need to be able to measure, practice for doing the trapezoidal rule, and they don't measure very well. Someone at lunchtime said to me they don't know when they pick up a ruler which side of it to use, which are the centimetres and which are the inches side. So we do need to practice them at those skills. So they certainly need to get the dimensions. Can I go back to what you were saying at the back? What is a cuboid made up of, really? You were saying it. See, all right, 6 faces, fair enough. But what about the 6 faces? Okay, they're rectangles. Say that again. So they're coming in 3 pairs. There's 2 which are equal. Yeah. Give me another word. Identical. Give me the maths word. Congruent. And there's a misconception possibly. How many people think congruent is a word you only use for triangles? Congruent triangles, and you have ASA and SAS and RHS and all that stuff. Congruent is for identical in all respects, no matter what we're talking about. So what is our cuboid actually made up of? 3 pairs of congruent faces. What will happen if we made the net of that to the congruent faces? Where will the congruent faces be located on the net? I have a sweet tooth, folks. Where are the congruent faces? Well, they're certainly not, because when I fold them, they have to be opposite. So now keep all that in mind, because what I'm going to do is I'm going to show you some work that the students did, and I want you to tell me, are they correct nets of the juice box, or if they are incorrect, what's wrong with them? So what about that one? It certainly looks correct. You've got your kind of cross shape, but there's a head shaking at the back of the room. What's wrong?
Well, from here it looks like two ends of squares. Black squares.
And they shouldn't look. So they got the net idea correct, the cross, if you like, but their measurement, what matches up with what two things will go together to form an edge, they had difficulty with. And some students couldn't see that was wrong until I cut it out and said, here, try and fold it. And it was only then, and it's back to the idea that this sort of three-dimensional stuff does really need to be done very hands-on. A lot of 12, 13, 14-year-old students and people like me who have just terrible spatial perception need the hands-on. What about that? Now, I don't know, does it show up that great up there?
The four things.
Yes, the four across the middle are congruent, and they're only meant to be in pairs. So that's wrong with that one. Oh, God help us, lads. Oh, Jeannie. I mean, you know, hold on a second. Fold it, fold it, fold it. And I didn't know what to do with it after that. And the first day that I was given the presentation, a teacher said to me, Tony, cut along the fold. And I did. Then I saw something that I couldn't see, that this student saw. Sure, to make a box, lads, you have to have flaps. I looked at that and I thought, not a very bright student. And then I suddenly find out they have 3D perception way in advance of mine. Be very careful how we react to students' problem-solving techniques. Just because they do something different to us, it could be brilliant. They might have said 2 + 3 is 5 inside in the middle of it and got the wrong answer. But the strategy could be brilliant. Now, who's at fault here? Is possibly me, the teacher. Did I make it clear that when we're drawing a net, we're not including flaps? And equally well, a problem could be coming from the primary school curriculum. I didn't point it out. I don't know whether anybody saw it or not. But when it mentioned nets, it said including flaps. So they were coming in from primary, including the flaps, and we are not. Now, I wish the syllabi were kind of uniform, if you like, but so that isn't the disaster that we all might have thought it was initially. No, it's still wrong, but, and God help us. Look at this. Now, my colleagues were very tough on this because they said a cuboid has 6 faces and that has 7. And one of them is totally detached from the others. I kind of read this as that was a mistake and they never crossed it out, because I'm generous by nature. But even if that's the interpretation, what's wrong? Well, clearly there should be pairs of congruent sides. What's matching this one? Where should the matcher for this one be, did we say? Certainly not touching it. So it can't be there or there or there or there, so it has to be, oh my God. And look, obviously, as we try to fold it. An open juice box. That one. Do you know what's gas like? As teachers, we have to look at these and see what's wrong with them, if they're wrong. And maybe we need practice too. What's wrong with that one? The hinge point certainly is going to cause a problem, but also 2 congruent faces alongside each other, 2 congruent faces alongside each other. And then you got this. Can you see it? It was an effort at making some sort of 3D representation. Again, is the teacher the one at fault here? Did I make it clear that it is a straightforward 2D representation without any, you know, or should I be telling them anything? Should I just give them the juice box and the scissors, cut it up, see what it is, and if they cut it up and flatten it out and hands-on with it, will a lot of those things be realised?
I think it'd have a lot more fun than saying nothing to them.
I agree with you, and a lot more learning. So moving on from there, how would I teach my students, if you like, to draw a net of a cuboid, an accurate net? So I kind of thought to myself, well, the first thing they'll have to get anyway is the measurements. Secondly, we probably would need to identify the congruent faces. We need to understand where the congruent faces go in relation to each other. We can identify whatever way we like with colours, with labels. Now, let's give us a strategy for drawing it. And I suppose, look, if the juice box is kind of sitting on the desk, and this is kind of back to what you were saying again, look, okay, that's the base is on the bottom, so I think maybe that's the first thing I'll tell them to draw. Now what will we draw? The two laterals, then the front and the back, or vice versa. And don't forget, now where's the top going? Wherever you have space, I suppose. But like, it can actually go in any of the 4 positions. So don't forget it. Now, Cheerios. Oh yeah. I had only small lunch, so I'll probably have a quick bowl of Cheerios when I finish up. By the way, lads, what's the dimensions of the box? Height? 34.5. Across the top? 24.5. Here? 9, spot on. Even with a very short bit of practice, you're hitting those very well. Think of how much the students will improve with just every now and then. Do you remember that question? And that's why I'm on about measurements. Estimate the height of a man, and on the basis of that, then they had to work with the silo. But like, you got answers for the height of the man as 20 meters, 2,000 centimeters, 2 meters, 0.2 of a meter. Now they gave him, in the exam, they would give him a very wide latitude and margin of error, but like, there's no one going to get marks for 20 meters or 0.2 of a meter. So estimation skills are on the syllabus. They are very important now, and we must engage our students with them. Anyway, go back to my Cheerios box. You gave me the dimensions. What did we say they were again? 34.5, 24.5 and 9. But now, not everybody in my group likes Cheerios. Some of them much prefer Coco Pops. So I asked them to estimate the dimensions of the Coco Pops box that's there. And 2 students, Jessica, gave me 6, 20 and 30. And John gave me 2, 4 and 12. They're both wrong. But if I can use bad English, one of them is more wrong than the other. Who's more wrong? Jessica or John? I heard John, did I? Jessica's more wrong. Why? An 800 gram box, the Coco Pops, is a 35 gram box. Now, you might say it's a bit unfair in the sense that they're not drawn to the same scale, but I've told you we've seen that in papers. They have got stuff that are not drawn to scale. It's also teaching the students to take everything into account. Go back to the cone example earlier on. The radius was wrong one time, the height was what we were working on the other time. So it's just a mechanism to teach the students to take everything into account. I'm not necessarily saying that's coming up as an exam question or anything like that, but I'm saying it's a strategy I might use in class to help my students estimate dimensions, take all aspects of a question into account in a kind of a fun, enjoyable, sort of interactive way. Now, I have a job for you. Homer got a job in the box factory one time, and he was responsible for making cubed boxes. So what I want to do is, in your packs there's one of Homer's templates, and I want you with the scissors, be careful will you, to cut out a cube where one of those squares is a face. First thing, I've gathered the rubbish from my previous workshops, and lads, let's look at crosses. But I was in Limerick, and it does fold. And I was in Cork, and I was in Athlone, and I was in Castlebar, and I was in Blackrock, and I won't say where I was, because that one won't do the job. But now, so what's the issue here? I think there's a couple of, why is everybody nearly all doing crosses?
You just said moments ago, start with the base.
You're conditioned, and I almost conditioned you by the way I taught you how to draw the net. And can I borrow this one? I really love to see, it's not finished.
We were going to change it, so.
You're going to try and change it. But I love the idea. They were actually doing what we were saying. They actually identified the top, the bottom, the sides, the front and back. I thought that was nice to kind of see as well. But the thing is, they only have to be able to draw a net of a cube or a cuboid one way. But they have to be able to recognize that could form a cube. Where is it? The other one. That will form a cube. That won't form a cube. So I suppose it begs the question, how many nets of a cube are there, and what do they look like? And there they are. There's 11 of them. And there's a GeoGebra file on our website that shows those very, very nicely. I'd just like you to see it. There's the cube. If you use the red slider, if I could get insert text away, it'll actually open the cube out. If you use the blue slider, you'll get the 11 different nets that there are. You can choose to close it at any given time. And if you use the little red one here, you can actually rotate it. So I think it's a very good teaching aid for cubes. Now, equally well, what I think is just as effective is the polydrons. If some student says to me that pattern won't make a cube here, there's 6 of them, put them together in that pattern and see if it falls. But they could need to know that this will or will not form a cube.
Did you say that was on the website?
That's on the Project Maths website, the Workshop 9 tab. And all of the GeoGebra files and resources that I've used today are on the website, Workshop 9 tab. So maybe possible questions that they might get. What shape is on the face opposite the circle? It is the smiley, isn't it? Now, if your students are having trouble, they have cube nets in front of them. Draw the shapes on them and get them to fold it. And interestingly, you see the way I set up the question with a cross? because I know most of them have drawn a cross anyway. And what about the few who didn't draw a cross? Well, I've loads here that I prepared earlier, like Doreen Allen. What shape are next to the circle? As a matter of fact, everything except what is opposite. If they have a problem, draw it. What shape is the arrow pointing to? It will be the square. Which shape is not next to the square? The one that's opposite it. Now, oh, there's a dice. Oh. Supposing I said to you, on your cubes, lads, turn them into dice. Put on the numbers for the dice. A die is mentioned on the syllabus in the Strand 1 section. So for that reason, I would be inclined to think my students should know all there is to know about a die. And opposite faces add to 7, I think I'd make sure they knew it. Just as well as I'd make sure they know what numbers are on a die. 1 to 6, describe them. You could call them natural numbers. There are odd numbers and even numbers. There are prime numbers and composite numbers. Are there numbers which are neither prime nor composite on it? 1. So what is the probability when I roll a dice that I will get a number which is neither prime nor composite? You know, I'd be working all those properties in. I have a job for you now. What I want you to do for me, in your packs, there's a sheet of coloured paper. You have scissors, you have rulers, you have compasses. I want you to draw a party hat in the shape of a cone that has a radius of 5 and a perpendicular height of 12. What are you drawing? No, sorry. What are you making?
Party.
You're making a party. So what are you making? A cone. So you're making a cone. Look, here's the cone. You're making that. What are its dimensions? Its perpendicular height is 12. Its radius is 5. What are you drawing? So what you're drawing, the net of a cone. And what does the net of a cone look like? Well, it's a section of the circle. It mightn't be semi, it depends on the... So you're drawing the net. But look, what's the radius of the net?
The slant height.
It's actually the slant height. Do you see it? Which, if you use Pythagoras, is... So there's a bit of Pythagoras' theorem there. So this will be 13 and this will be 13. Now the question is, how big is that? And what makes that up? The circumference of the... So the length of that arc, what's the length of an arc? Is it r theta? Where theta is in radians. And r is? But what makes that up? The circumference of the hat, which is the circumference here, which is 2 pi r, which is 2 pi 5, which is 10 pi. So 13 theta has to be equal to 10 pi. So theta, the angle in the net, is 10 pi over 13. And if you're going to use a protractor, you need to convert that back into degrees, and pi is 180, and it comes out approximately 138 degrees. So now radius 13, protractor 138 degrees, radius. You might go an extra bit to allow for a flap so that you can actually fold it over and what? You went a bit too far. I have mine here, but I'm afraid it's a bit battered and worn from use. And I just stapled it together there. I think that one looks to me marginally too big. That one looks a bit better. But lads, that looked like a very easy, foolish question. And it has a huge amount of maths in it. Now, that's the kind of activity, again, it's down in, we kind of maybe intended it as a one lesson activity. I'd nearly rather give it to a class and say, come back to me in a week with it. And let them be puzzling the maths out and chatting to each other about it. TY, great exercise in TY maybe, but you have a lot of maths there. So our first activity is inputting a function. So we'll input a cubic function, and the function will be inputted in the input bar at the bottom of the screen. So we have function f of x equals x to the power of 3 minus 4x squared, 4x to the power of 2 plus 8x minus 12. Hit the enter bar and the function is drawn. Now in this case we can't actually see the entire cubic, so I will highlight the cross on the right hand side of the toolbar, and on the graphics screen roll the mouse to zoom in closer to the function. And now if I want a better view of that, I can change the scale on the x-axis by locating the cursor on the axis, left click, hold and drag to increase the scale and get a better view of what the cubic function actually looks like. Equally well, I can change the scale on the y-axis by doing likewise. If we want to change the appearance of the function, with the arrow on the left side of the toolbar highlighted, point to the function, right click and scroll down to the Object Properties option. And down there I have the option to change certain characteristics of the function. For example, if I look in the Basic tab, I can opt to show the label or hide the label of the function. And I have the option to just display the name, which would be f, or the name and the value, which is f of x equals x cubed minus 4x squared plus 8x minus 12, and that's appearing down there at the bottom of the screen. Equally well, I can choose just to have the value appear, or I can choose caption, in which case I would write a suitable caption on the caption area, and that's what will be displayed. So I think in this case I'll return it back to name and value. I can change the color of the function by clicking the color tab and choosing whichever color I intend to use. I can change the style of the function by dragging this pointer, which will thicken up the line representing the function. And I can change the line style by taking this option here with the drop-down menu. That I would need to be careful of, as in this particular case it is now a dashed line which would indicate discrete data, and that in fact would not be appropriate for demonstrating a function. However, could be very useful doing statistics. So I'll just point to the function, right click, object properties, and I will go back and take the line style option, which is continuous, to indicate continuous data. Now, to do the next activity, I will choose a new window. In this new window, I do not have the grid available to me at the moment, so if I point to the drop-down arrow alongside graphics, I get the toolbar that will indicate the grid. So if I click on the grid and highlight it, I have my grid background yet again. Now in this activity, I want to draw a function, but this time I want to draw it within a particular domain. So I will use a particular command called function, and the easiest way to do this is if I start to type the word function, a drop-down menu will appear where it says function, start value and end value. So I'll click on that, and whilst the function is highlighted in blue, I'll key in the function there. In this case, a quadratic, let's say 2x to the power of 2 minus 2x minus 5. Use the right arrow to move over to the field indicating start value, and let's say the beginning of my domain is -2, and I will use the right arrow to go over to the next field for the end value, the end of the domain, and let's say that's a value of 3. Press the enter key and the function appears on the graphic screen. In this case, you cannot actually see that the function does begin and end. So again, if I highlight the cross on the right hand side on the graphic screen, left click, hold and drag, now I can actually see that the function does begin at an x value of -2 and end at an x value of 3. By rolling the wheel, I can change the zoom to see the whole function, and again, as previously demonstrated, if I locate the cursor on the x-axis, left click and drag, I can change the scale to change the appearance of the graph. Another method of labeling the graph is to actually indicate the function here in the algebra view. Left click, hold, the arrow needs to be highlighted, point to the function in the algebra view, left click, hold and drag, and that will actually bring the label for the function over onto the graphics screen. If I now want to find an intersection of that function and another function, let's draw another function. For example, x equals 1.4, and that draws in the function which is a line parallel to the y-axis through an x coordinate of 1.4. To find the point of intersection, so of those two functions, I need the intersection tool, which is not visible on the toolbar at the moment, but what I must realize is that each tool on the toolbar has a drop-down menu in the right-hand corner. So if I click that there on the second one, I'll find the intersect two objects. So I choose that, and then indicate the two objects that you want to find the point of intersection of. The quadratic, click, the 9, click, and A is demonstrated on the graphic screen as the point of intersection, and over in the algebra view I can see the actual coordinates of that particular point. The next activity is to show how to move a diagram from Geogebra screen into PowerPoint or Word. And to do that, I'm going to use the snipping tool, which is a feature of Windows. So I'll go out onto my Windows, highlight the snipping tool, and then just left click and drag a rectangular box around the area that I want to cut out of the GeoGebra screen. Now I will go into either Word or PowerPoint. So in this case, I think I'll choose PowerPoint. And I can paste the picture of the screen into my slide or into my Word document for use as an exercise sheet or examination question as desired.